Hi everyone, Mr. H here. We're now going to look at some applications of completing the square. We're going to have two goals today. One is to graph a parabola originally in standard form by first completing the square. And secondly, we want to apply this concept to projectiles, business, profit, and cost, and similar situations. So let's look at a projectile example. A projectile is any object that flies through the air on its own, so it follows a parabolic path. For example, if you kick a football, excuse me, it's going to follow roughly this projectile motion. Now there's some air resistance, but we're going to assume that if we didn't have any air resistance or if it was minimal, it's going to follow almost perfectly a projectile. And so there are actually two ways we can model this. There's one way, which is modeling the vertical height versus the horizontal distance. So you could say that this is measuring how high the ball goes versus how far it goes. We could also measure it in terms of time instead of horizontal distance, vertical height and time. And so we would, instead of use x, we would use the variable t for time. And we could instead, on the x-axis, model how long it takes for the ball to get to the maximum point and then come back down to the ground. And those two graphs are actually going to look different, but as we'll see, the highest point that they reach should be the same. And we're going to graph both of these and we're going to compare them and see. So part A says, in the first case, what's the maximum height of the rocket? Now, technically speaking, a rocket is has a self-propulsion system as it's going through the air. So technically speaking, a rocket isn't a true projectile, but oftentimes we'll see a question will say it's a rocket, even though we know it's not really a true projectile. So we're going to go with rocket here, but it could be a rocket, it could be a ball, it could be anything that's flying on by itself through the air. So the maximum height of the rocket, how far has it traveled horizontally when the maximum height is reached? And then in the second case, again, maximum height, after how many seconds will this occur? So I hope that's clear to you that what you need to do is you need to complete the square for these. So let's go ahead and do that for the first one. So for the first case, we had y, or h, equals negative x squared plus 8x plus 4. And so what we need to do is just like we've done before, is we're going to common factor out the negative 1 only. And we're going to be left with x squared minus 8x plus 4. Then we're going to take this number 8, divide it by 2, and square it. That gives me 4 squared. That's going to give me 16. So I'm going to go ahead and I'm going to add and subtract that number inside the brackets. And then I need to multiply the negative 1 times the last term in the brackets. It's going to give me positive 16. And finally, I'm going to be able to combine the 16 and the 4, and I'm going to be able to factor the x squared minus 8x plus 16. This gives me x minus 4 all squared and plus 20. Well, the question asked us for the maximum height of the rocket, and we know then that the maximum height has to be this. That's the maximum height is the k value. And how far horizontally will this occur? Well, it's going to occur at the h value. The h value is the, in this case, the horizontal distance traveled at the vertex, or when it gets to its highest point. All right, so we know that that's the case, and we also know that we can graph this with a few pieces of information. So let's go height here in terms of meters, and we'll go the horizontal distance in terms of meters. And we know that the vertex is at 420 right there. We also know one other piece of information. If you remember, the c value in this original form, the standard form, if you just need a quick reminder of what standard form is, it's y equals ax squared plus bx plus c. So that c value, that last number, indicates the y-intercept. So the c value in standard form is the y-intercept. And so we're going to go find that y-intercept of 4 right there. And then we can use some symmetry here, because that's the axis of symmetry. And we can say, well, that y-intercept is 4 to the left of that. So if we go 4 to the right of that axis of symmetry, and I put another point at the exact same height, You guys can see there I'm going 4 to the right of that axis of symmetry. So I have those 3 points on my graph now, and what I can see is if I draw a curve between those points, my parabola is going to look something roughly like that. And so we can see here that it's going to hit the ground after about 8.5 meters. And I know that my maximum height is 20 meters. And so we could just note that max height in answer to that first question is 20 meters. And I also know that the horizontal distance of that max height is 4 meters at the max height. And then as we noted already, we have this point 0,4, which is the y-intercept. All right, so that has allowed us to graph that and to be able to answer everything there. And all we really had to do is complete the square in order to have all that information at our fingertips. Let's look at the second case now that instead of dealing with horizontal distance, deals with time. So the question in the second case said h equals negative 5t squared plus 17.9t plus 4. Now, a couple of things jump out to you here. First thing that I want to mention is just in regards to this coefficient of negative 5. Technically speaking, if an object is flying through the air, the a value is negative 4.9. That has to do with some of the calculus around how parabolas actually fly. We're often going to see it rounded to negative 5, but technically speaking, it is negative 4.9. The second thing I want to deal with here is this 17.9. You're going, well, that's an ugly number. How are we supposed to do that? You just go ahead and do the same steps you've done before, but you're just going to have some decimals to go with. So nothing really has changed. It just gets a little uglier in this one. So what we're going to do is we're going to common factor the negative 5 out of the first two terms. So the negative 5 out of the first one gives me a t squared, and then I'm going to divide 17.9 by negative 5, and what I get is negative 3.58t. It's left over. Told you it was ugly. 3.58 divided by 2, which is the magic number as we've always done, squared, gives me 1.79 squared, which gives me a value of 3.2041. 3.2041. So we go ahead and we add and subtract that in the brackets. Negative 5 t squared minus 3.58t. Adding that 3.2041. Subtracting that 3.2041. And then adding 4. Now we go ahead and we take that negative 5 out front and we multiply it by the last term in the brackets. And I get almost exactly 20. Very close to 20. I get 16.0205. I say close to 20 because we added to the 4 to get the 20 here. So negative 5. And then remember, the square root of 3.2041, well, that's this number up here, 1.79. So it's t minus, because that sign's a negative, minus 1.79 all squared, plus 20.0205. Now, if we actually round that to something that makes it a little bit easier to graph or clear to graph, we would round it to negative 5 t minus 1.8 all squared plus 20. And so this is the thing that I want to graph here and just compare with the other one. So we had this originally from the previous equation, and now we have this new one down at the bottom. So if I graph this, again, I'm going to go h in terms of meters, but on the x-axis here, I'm going to go time in terms of seconds. And I'm going to graph 1.8 and 20. 1.8 and 20 is right about there. And I'm going to graph the y-intercept, which is this right here, which again was 4. And then I can use the symmetry, and I can say, well, because this distance here is 1.8, if I go across 1.8 more to 3.6, I can graph a point right about there at 3.6 and 4. And I had this y-intercept at 0 and 4. and I have the vertex at 1.8 and 20. And if I draw a curve through that, what we can see is that it's going to hit the ground somewhere close to 4 seconds. We don't know what that number is exactly yet. We're going to do that in our next unit. But it's going to hit somewhere around 4 seconds. We know that its maximum height is going to occur of 20 meters. And we know it's going to reach that after 1.8 seconds. And so these two things actually represent the exact same projectile, but they're doing it from two different perspectives. Notice they're both having a maximum height of 20 meters. Now you might say, well, Mr. Hamilton, this was 20.0205. The reason for that is I can't get them exactly the same. I took the numbers that were rounded somewhat, but for all intents and purposes, those are the same heights. And though that's the same, obviously what's happening on the x-axis is different. On the x-axis in the first case, remember that's the horizontal distance, and in the second case, that's time. And anytime you have to deal with this situation where you're doing height versus time, we're going to have an a value in the equation of -5 or -4.9, which is relatively large. It's a relatively large vertical stretch. And that's what's going to give you a graph that hits 0 earlier. It hits the ground. It looks earlier than the other case, but it's just representing a whole different thing altogether. So let's look at one more example, and that is business profit. This question says the profit that a Frisbee business makes is related to the number of Frisbees that it sells. If it sells too many Frisbees, it will have an increased cost and decreased profit, since it will have to increase the size of its facility. If it sells too few Frisbees, they will not bring in as much money to pay for their current facility. An efficiency consultant models their profit by the equation P equals -4x squared plus 48x minus 44, where x is the number of Frisbees sold in thousands, and that's important, keep that in mind, and P is the amount of money or profit made in thousands of dollars. Again, keep in mind the thousands. How many Frisbees do they need to sell to have their max profit? How much will this maximum profit be? Graph the relation clearly showing the maximum. So let's take this equation, and what I want you to do is I want you to pause the video, and I want you to try to go ahead and complete the square on this, and then compare your answer to what I get. So this is what you should have gotten, and you'll notice that this is, in every single case we've looked at so far today, this is a negative. And the reason that's a negative is because when you take the vertex out of that, if you didn't have an x minus something, you would have an x value of the vertex that was negative, which just wouldn't make sense in terms of profit or number sold or amount of time or horizontal distance. Those are all positive values, so we need to make sure that we get a negative when we complete the square. So that means that the vertex is at 6 and 100 here. That does not mean you're selling only 6 Frisbees and making $100. We conclude they must sell 6,000 Frisbees, because this was telling us in thousands, to maximize the profit, and that maximum profit is $100,000. So let's graph this and see what this actually looks like down below. So as we noted that at 6,000, this is the number sold. So 6,000, we have $100,000 in profits. This is the profit in thousands of dollars. And this is the number sold in thousands. And we also know that it was at -44 down here. From the original standard form, that was the y-intercept. And so if we go ahead and we use the axis of symmetry, we go over to -44 and 12, or 12 and -44 rather, and we can graph that looking something like this. Now we get these points. We get 0, -44, 12, -44, and 6, 100,000. And obviously we want to sell 6,000 Frisbees, but if we sell less than, looks about 750 Frisbees, we actually lose money. And if we sell more than about 11,250 Frisbees, we lose money.